warahmatullahi wabarakatuh. Selamat pagi. It is honor to chair this session. So in this session number 7, we have three contributed papers presentation. So as for each presenters, it has a 15-minute presentation time and 12 minutes for presentation and 3 minutes for question and answer. So the first presenter, I would like to invite Dr. Siti Aisyah Reduan from University Malaya, Malaysia. She will present a presentation with the title Q switches pulse generation with a copper telluride as saturable absorber in L-band erbium doped fiber laser cavity. Okay, please, time is yours.
Okay, thank you. I share my screen. Okay, can you see my slideshow?
Yes, we can see the slide.
Okay. All right. Hi, good afternoon. My name is Siti Aisyah. I'm from Photonic Research Center, University Malaya, Malaysia. Okay.
Could you please speak up your
Okay.
voice?
Okay.
The
Can you
volume.
hear me? Okay. Hi. Hi. Good afternoon, everyone. My name is Siti Aisyah. I'm a research officer from Photonic Research Center, University Malaya, Malaysia. So for today, I will present my work with the title of Q-switch pulse generation with Cooper Telluride SSA in L-band erbium doped fiber laser cavity. Okay, before I proceed with my work, I will briefly share the history of fiber laser. So the fiber lasers start in 1961 and have a recent development throughout the years. There is intensive interest in fiber laser. This is due to the advantages of the system, which is have a high efficiency system, easy beam delivery, and alignment-free design. There are a lot of applications based on fiber laser. One of it is telecommunication, medicine, and laser machining. The table shows the relationship of band names and optical wavelength band. In this work, we focus on the region of L band, which cover a region 5 nanometer. A Q-switch pulses based on fiber laser system, where the Q-switch pulse can be either generated by using active or passive element or device. However, active Q-switch fiber laser uses a bulky and expensive device compared to the passive fiber laser, which utilize much cheaper, more compact device and widely used. And in this study, we generate a passive Q switch that is seen to have advantages due to their lower fabrication cost, as well as compact and robust form factors, in addition to having a significant system integration and operation flexibility. In this work, we use a saturable absorber by inserted into the laser system to generate the passive pulse laser in the system. There is a significant progress has been made by generate the passive Q-switch pulses with the potential materials such as other materials as a saturable absorber, and that having proven to be able to generate a high performance passively Q-switch pulses from fiber laser cavity. Okay. The next slide shows the evolution of saturable absorber. In 1960s, the researcher used dye or colored classes and proceed to the SESAM and with the zero dimensional, and there is a recent use another material as a saturable absorber, and recently there are researchers that using topological insulator, transition metallic carbonides, and black phosphorus. Okay, there are a few types of materials that have been studied to satisfy the criteria as a saturated bed absorber, such as SESAMs and single-wall carbon nanotube. However, SESAM have difficulty to compatible with other fiber, whereas single-wall carbon nanotube is hardly to fabricate and costly. Therefore, there are many paper has reported passively Q-switching operation by employing one of the group, which is known as transition metal bicarbonate or TMB, as a saturated bed absorber since the pulse generation, especially Q-switch pulse at the broadband wavelength is easier due to the ease of fabrication, compatibility with the fiber in the cavity, high absorption, and nonlinear optical response. One of the material is copper telluride, which is used in this work, which has a promising characteristic. One of it is high thermal power values and has a bit remarkable optical properties that perfectly fit for application in the photonic field. Okay, in this study, we prepare and characterization of the copper telluride, where we use 100 mg of copper telluride powder that is dispersed in the 10 ml of the ionized water in bus sonicator for 10 hours to exfoliate the copper telluride from epochs, thus forming the few layer of the material solution. After the sonication process, the solution was centrifuged for 10 minutes in order to collect the supernatant, which consists of few layers of copper telluride sample. The solution was further used to fabricate the copper telluride polyvinyl alcohol film using simple casting method, where we process the 100 mg of PVA powder by dissolve in 10 ml of deionized water to prepare 10 ml of PVA under vigorous stirring by keeping the temperature constant at 60 degrees Celsius on the hot plate for 2 hours. Following this, the copper telluride solution was mixed with the previous PVA solution with the ratio of 1:9 ratio while stirring at the same temperature for 15 minutes. Then the mixture was transferred into a glass petri dish and evaporated for 24 hours. Okay, then to form the SA film. And we characterize the non-linear optical properties of the saturated bed absorber by using a twin detection method. The graph shows the nonlinear saturated bed absorption of the material, where the information we got is on modulation depth with a percentage of 28% and saturation intensity of 0.6 kilowatt per cm squared. Okay, we proceed with the experimental result discussion. As we can see in this work, we use 2 meters of leaky carbon fiber as a gain medium, and then forward pump by 976 nanometer laser diode, and connected to the 980-1550 nanometer WDM coupler to ensure there is unidirectional operation of the light propagate in the system. We use an isolator. For this work, we use 2080 optical coupler, where 80% of the signal was connected back into the cavity, and 20% of the signal is directed to 3 dB coupler for collecting the output data. For the pulse, to generate the pulse laser, we insert the thin film saturated bed absorber by sandwich it between the ferrules of the optical adapter, as we can see from the figure. To collect the output parameter, we use an oscilloscope, photodetector, and optical spectrum analyzer, as well as the radio frequency spectrum analyzer to study the pulse stream, to monitor the optical spectrum and measure the SNR value. We also use an optical power meter to monitor the output power of the pulse respectively. Okay, we proceed with the experimental result and discussion. The slide shows the figure of the typical characteristic of the key switch pulses. As In the study, the self-start Q switch pulse operate at the pump power of 260.3 milliwatt, and which is also known as Q switching threshold. And we can see that the central wavelength at the pump power of 400.3 milliamp is around 150 nanometer. And we can see that the for the next figure show the pulse train with the frequency of 40.1 kilohertz. And the SNR value of this pulses is around 44.2 dB. Where the next figure, the right hand side of the figure shows the trend of repetition rate and pulse width over the pump power. At the highest pump power, which is at 400.3 milliwatt, the repetition rate increased from 28 kilohertz to 40.1 kilohertz. In contrast, the highest pulse width recorded is 48 microsecond, decreases throughout the pump power to 2.1 microsecond. And the both for the trend for peak pulse energy and output power have a similar trend as the repetition rate with the increasing pump power. The minimum output power is around 0.45 milliwatt and rise to 1.36 milliwatt at the maximum pump power. And as we can see from the figure, the maximum pulse energy is around 0.03 nanojoule. Okay, so for this, the conclusion of this work is that in this paper, a passively Q switch EDR fiber laser can be operated in the L-band region by from the region of 1565 to 1625 nanometer for L-band region by using a copper telluride PVA film as a saturable absorber has been demonstrated. Where in this study, the Q switching operation start at 260.3 milliwatt until 400.3 milliwatt, which is the maximum pump power. As the pump power is tuned until 400.3 milliwatt, the output power increased from 0.45 milliwatt to 1.36 milliwatt at the central wavelength of 150 nanometer. And the same pattern of repetition rate is observed over the time where the maximum repetition rate is 40.1 kilohertz. The minimum pulse width and maximum pulse energy obtained is 2.1 microsecond and 0.03 nanojoule respectively. Q switching operation in this L-band cavity give a SNR value of 44.2 dB, which implying that the Q switching operation is in the stable state. And this can have a potential to perform greatly with the further cavity optimization. And this is the reference that have been referred for this study. Okay, I think this is the end of my presentation. Thank you.
Okay. Thank you, Dr. Siti Aisyah, for a nice presentation. So also it is on time for about 12 minutes. So I would like to invite questions from the audience. If you have a question, please raise your hand, or you can type the question in the chat room. Okay, yeah, we are waiting. So, Dr. Siti Aisyah, could you explain one important aspect for this saturable absorber is the power threshold. Do you have any idea how to reduce the power threshold for certain material?
Okay. As I doing my experiment, what I noticed that if we have to really focus on how to optimize the fabrication of the saturable absorber, because if we have a very low modulation depth, it's not a good value to generate a pulse laser. So we have to control the layer of the saturable absorber to get a moderate value of modulation depth. So we have to understand how to fabricate the saturable absorber, especially in the if you want to insert into the laser cavity. Yeah.
What kind of method do you have?
For this work, we prepare to be a saturable absorber in terms of film. There is another method that we use for as a saturable absorber, such as deposition, where we deposit the material on the fiber ferrules as a liquid instead of film, but it's not really good as a film, because if we put a liquid, it become evaporate faster as compared to film. For film, we can use repeatedly for the next experiment, so it can be repeatable as
Okay, yeah.
compared to the liquid. Yeah.
Okay, so there are two questions in the chat room. The
Yeah.
first one is from Dr. Ahmad. What is the reason using PVA? Because the PVA is not really transparent and may disturb the coherent beam properties.
As we have made an experiment, which is we check the absorption of the PVA is nearly zero. It's not that exactly zero, but it's nearly zero. So it's not a huge effect on the material. So we use the PVA itself. But that's I mentioned in previous, there is cons and pros where we can use the material itself, or we choose the PVA as a base to make a material as a film, and we have to know how to fabricate the good saturable absorber and how to control the SE. Yeah.
Okay, thank you. And then the second question from Professor Martin. Now you have studied it, and what is the advantages this material or other materials?
Okay. As copper telluride is one of the material in the transition metal decagonite. So as we have made a review by refer from other paper, it seems that copper telluride has a high thermal power values and has a bit remarkable optical property that is perfect for photonic field. Especially it can withstand thermal damage higher than other material.
Okay, thank you, Dr. Siti Aisyah. We have end up this presentation, and thank you, and give a big applause to the first presenter.
Thank you.